Hello, and today we're going to solve trig equations with domain restrictions. So we're going to be told that x has to be between some values and have to solve that way. That actually comes in very handy later when we solve triangles. So to solve with restrictions on x, you would solve it normally using the infinite case as your solution, and then you would choose values of n, that integer, to give x values within the restriction. So let's take a look at how to do that. Alright, here we're solving for when x is between 0 and 360 degrees. We have three different trig functions: tangent of x, secant of x, and 2 times the tangent of x. Looks like nothing reduces by using Pythagorean identities, reciprocal identities. So it looks like we're going to have to set this equal to 0 and factor. Let's do that. Tangent of x times secant of x minus 2 tangent of x is equal to 0. We can factor out a tangent of x from both of those terms, so we get secant x minus 2 is equal to 0. And if we set each of these equal to 0, we'll get tangent of x is equal to 0. And if we set secant x minus 2 equal to 0 and add 2 to both sides, we'll get secant x is equal to 2. Alrighty, let's take a look at our unit circle and see what's happening here. Tangent of x is equal to 0 where? That's here and here. They're equidistant from each other. So if we start here at 0 and continually add pi, or 180, then we would end up with all the solutions. So whatever we're taking the tangent of, here it's x, is equal to 180 degrees times n. You can go as many times as you want. That is not a restricted value for secant. Secant's only restricted where cosine is 0, which is at pi over 2, and 3 pi over 2. Tangent and secant have the same restriction. So if we solve for one, we're not going to have to worry about being in the domain restriction of the other, which is nice. All right, secant of x is equal to 2, where x is 1/2. That happens up here at 60 degrees, and that happens down here at 300 degrees. They're not equidistant from each other, so we'd have to set up two different equations. X is equal to 60 degrees plus 360n, and x is equal to 300 degrees plus 360n. Alright, so we've solved for every single possible angle ever that would satisfy the equation, but now we need to just restrict our x's between 0 and 360. So let's start with this equation. If we choose 0 as a value for n, we'll end up getting x is equal to 0, which is perfectly fine. If we choose 1 as a value for n, we'll get 180 degrees, which is fine. And if we choose 2 as a value of n, we'll get 360 degrees, which is fine as well, because all these values are inside of this interval, which is inclusive of 0 and 360. Alright, if we look at this equation, if we choose a value of 0 for n, we get 60 degrees, and anything bigger would get us an angle that's outside of our restriction. Okay. Down here, if we chose n as 0, again, we get 300 degrees. And again, anything other than 0 would give us values outside of the restriction. So here are the 5 angles that would satisfy this restriction, but then also are solutions to this equation. Okay. So again, just to clarify, we're picking integers for n and then collecting all of the values of x that actually fit this restriction. Let's take a look at a different one. Ooh, nice. We have one trig function, so we can just isolate it and then solve. Let's divide both sides by 2. So sine of 3x is equal to root 2 over 2. Sine doesn't have any domain restriction, so no worries. So root 2 over 2 happens with sine in two locations, here and here. These are not equidistant from each other, going one way and going the other. So we're going to have to set up two different equations. So whatever we're taking the sine of here, it's 3x. 3x is equal to, the first angle is 45 degrees, so 45 degrees. Plus you can go in a circle as many times as you want. The second angle measurement would be 135 degrees. And again, you can go in a circle as many times as you want and end up at the same coterminal place where your sine of that angle would be root 2 over 2. Alright, let's isolate x by dividing everything by 3. So x is equal to, this would be 15 degrees plus 120 degrees n. Okay. Here we do the exact same thing. X is equal to 45 degrees plus 120 degrees n. And let's collect our discrete values down here by choosing values of n. If n was 0, 15 degrees would work. If n was 1, 135 degrees would work. And if n was 2, we'd be a little bit too big, because if n was 2, this would be 240 plus 15, and that's outside of this restriction. So we stop there. Now let's go to the other side. If n was 0, this would be 45 degrees. If n was 1, that's 120, right? If n was 1, this would be 165 degrees. Okay. And if n was 2, would be too big. So here are the 4 values that work, that satisfy this equation, but that are also in between 0 and 180, non-inclusive. Okay. One more to look at. Solve for theta if theta is between 0 and 2 pi. Okay, so in this case, they're asking us to solve in terms of pi, so that's what we're going to do. Alrighty, cosine square theta is equal to 1, so we'd square root both sides. We get the absolute value of cosine theta is equal to 1, which means that cosine theta is equal to positive and negative 1. Okay, where does that happen? That happens, positive 1 is here, negative 1 is here. Alrighty, so our infinite case is that we start at 0 and we keep adding pi over and over and over again until we get to a place where I guess we want to stop. So theta, what we're taking the cosine of, is equal to pi n. Any multiple of pi would be an angle that if you take the cosine of and square it, you'd get 1. Okay, so now we need to choose values of n so that we end up getting the thetas that are in the restriction. So if n was 0, theta would be 0 radians. If n was 1, this would be pi radians. If n was 2, this would be 2 pi, but 2 pi is non-inclusive. So these are the only 2 angles that theta are allowed to be given this restriction. Okay, so that's how you do it. You solve normally, and then you find values of n that would get you values of your angle that are within the restriction that you're given at the beginning. And that's the last piece of how you solve trig equations.